Howdy, it's Mr. Russell. Let's talk about Hess's law. It says that the sum of the enthalpy for the reaction is the same whether the reaction occurs in just one step or a whole bunch of steps, several steps. So it doesn't depend on the pathway or how many if it or how many steps it takes, or if it takes the first, third, or second pathway. There's a couple of guidelines that go along with this. Let me move my picture. The first guideline is if the reaction is reversed, the sign of delta H is reversed. So if it was negative before, it will now be a positive if we reverse the reaction. If it was positive, then we change it to a negative. And if the coefficients in the reaction are multiplied by some integer, we have to multiply the delta H by that integer. Show you what I mean in just a sec. Here we have an example of two very similar reactions where we have nitrogen and oxygen to yield to ultimately yield NO2. Here it occurs in two different steps, or two different pathways, here it only has 1 mole of oxygen to react with at the beginning to make NO, and then that NO reacts with another mole of oxygen to make NO2. On the right side, it goes from nitrogen plus 2 moles of oxygen right away to just go straight into NO2. I'll look at the right side of the screen first. This is just a one-step reaction where it goes from the reactants here, nitrogen and 2 moles of oxygen, and that makes 2 moles of NO2. Over here on the left side, we've got something a little interesting, because this is the reactants for the first equation. So I will circle those in yellow, and then I'll circle the products for the first equation here in red. So it jumped 180 kilojoules from here to here, and then it goes from in green, it goes from these are the reactants for the second equation, and then they go down to the products of the second equation here. So the reaction pathway actually started from here, and it went up 180 kilojoules, and then we subtracted 112 kilojoules. So there was an actual net gain of 68 kilojoules. Over here, since it only went one step, it's easy to see that it only went 68 kilojoules. So they're both the same. That's Hess's law. Let's do the following mathematical example. Given the following reactions and their respective enthalpy changes, calculate delta H for the reaction. 2C2 plus H2 yields C2H2. There we have three different reaction steps in our pathway and their corresponding enthalpy changes. So somehow I need to make these three steps look like my original equation, and using Hess's law. Watch out, because they will give you commonly they'll give you some steps, but they're not always in the right order. So don't presume that this is the first step. The first step is going to be carbon plus oxygen yields CO2. What I've done is I've just taken this step here, and this is this step, and notice that I multiplied it all by 2. Because of that second guideline that I gave you, I need to multiply its enthalpy by 2. So that's where that comes from. Now my second step is going to be hydrogen and oxygen yields water. And I just write down the corresponding enthalpy for that. Now the third step is going to be this one. Can you see which step it is? That's right. It is going. This is going to be this step. Notice that we reversed the pathway. So now this negative now became a positive here. So notice that this one is positive. By doing this, when I go through these, you can do this in these questions. There are two carbon dioxides and two carbon dioxides here, one on the right, one on the left, or two on the right, two on the left. There's one oxygen, one water on the left, and one water on the right. And there are 5 halves of oxygen on the left and 5 halves of oxygen on the right. So what I end up with is 2C2 plus H2 yields C2H2. Now all I have to do is type those into the calculator and type in the sum, and I get 226.7 kilojoules per mole. One more example of Hess's law. I want you to calculate the heat of combustion of carbon to carbon dioxide the heat of combustion of carbon to carbon dioxide is negative 393.5 kilojoules per mole of carbon dioxide. That means that 1 mole of carbon dioxide will release this much amount of heat. Whereas the combustion of carbon monoxide, the combustion of carbon monoxide to carbon dioxide is minus 283.0 kilojoules per mole of carbon dioxide. So calculate the combustion of carbon to carbon monoxide. So I take my original equation or my original problem from carbon, and I know that it's being combusted. So I know I'm adding oxygen to make CO2. And it releases this much heat. I know that carbon monoxide plus 1/2 oxygen yields CO2. And that releases this much heat. So you might be looking right now at this thing right here. I've told you in the past to never put a fraction as a coefficient, but for Hess's law and these thermochemical equations, it works out better if you put these fractions. The reason is because you need to have apologize, guys, the phone rang and I'm not exactly sure where I was. I do know I was right here at 1/2 oxygen, and I was explaining that it's important for thermochemical equations. Sorry about that. Okay, so we're just going to move on, and we're going to go ahead and move into writing down we're going to kind of rearrange the steps so that we can get to the final reaction that we're shooting for, which is carbon to carbon monoxide. So by doing this, we are going to take carbon dioxide and move to carbon monoxide, and we're actually going to switch this equation here, and we're going to turn it backwards. Remember, when we do that, we have to flip the signs. So when we do that, it works out that we end up with 1/2 of oxygen on the left. So we're still combusting carbon into carbon monoxide. And that gives us a final enthalpy of negative 110.5 kilojoules. So now I remember where I was with the before the phone rang. The moles of carbon dioxide, which is what we had in the beginning, we had that's the heat that is released when 1 mole of carbon dioxide is released or reacted. That means that we need to use the least number of reactants or possible, because we still want to keep a 1 in front of this carbon dioxide. That's the whole idea. Is we still want to keep this coefficient as a 1, so that's why we adjust the other coefficients to meet that. So if we need to make this a fraction, we'll go ahead and do that. That's totally allowed. I really hope that wasn't confusing, and apologize for the interruptions. So thanks for watching, y'all. That's Hess's Law.